So just like before, let me read through solutions and then we'll take questions. Sound good? So for 15, value, the solution is 1/2 meters per minute. For 16, the value is 3.5 meters squared per second. For number 17, it is -5/9 pi centimeters per minute. And then the last one is, I think it's 1/7 pi meters per minute. I had a on that one.
Isn't it 1/6 pi?
It should be 7 pi. Because it's only half a sphere that's underwater. Yeah, I had a half, or I had 6 on my work and I missed that it's a half a sphere underwater. Questions from you guys? Yeah, Frankie.
Could you do that problem?
Sure. I think again, this is I thought was the most challenging, largely because of the picture being kind of tough to visualize what's happening. So I'm going to just kind of start with a picture. So there's like my cylinder with the sphere in it and the water level. And what's happening here, it's too big, do this. Yeah. And now I've drawn it too high. Try that again. I'm going to break my cylinder. Do that. Just make it a little higher. Come on. Ooh, sorry guys. Okay, so like as the water is getting deeper, the sphere is expanding. Is everybody okay there? So call that the radius of the sphere. And I'll call this like the height of the water. Is everybody okay there? So let's start identifying some parameters. So what are the things that are changing here in this?
The radius of the diameter.
The radius of the sphere is a variable. The volume of what? You said volume. The what? The tank? Well, the volume of the tank is constant. The tank isn't changing size. But the volume of the water is changing, right? Because we're dumping water in. The volume of the sphere is changing, right? And if that sphere wasn't there, what would the shape of the water be? A cylinder. So I'm also going to think about the volume of that hypothetical cylinder of water as well. Because what's the relationship between the water in the tank, the cylinder of water, and the sphere? All right, if I think about the shape of the water, what it actually looks like is a cylinder with half of a sphere like cut out from it. Because the sphere is sitting in the water and taking up some of the space the water would like to fill. Now, I don't know how to calculate the volume of like a cylinder with a sphere cut out of it directly. So I'm going to think about like no sphere cut out and then cut that half a sphere out. Does that make sense, Frankie?
Mm-hmm.
Coming up with that is the hardest part. Like getting a good picture of what's going on and going, okay, well, how do I relate the volume of the water to what I've got going on here? Also worth noting, the radius of the sphere is going to be the same thing as the height of that water. And that's what we're asked for. How fast is the depth of the water changing when the height is, when the depth is 1. So I'm going to generate some differentials here, right? Actually, I'm not going to bother. I'm not going to write this. I'm going to write, oops, I do want that though. I'm going to write that. I think those are all the variables, right? So the thing that's changing is the volume of the water. So that's going to be the volume of the cylinder of water minus the volume of the sphere, right? Yes, thank you. Got it. So the volume of a cylinder is pi r squared height, right? Now keep in mind that that radius of the cylinder of water is just going to be the same as the radius for the tank. That's a constant, which is nice. The volume for a sphere is 4/3 pi r cubed. Now the radius of the sphere we know is the same as the height of the water. So even though we don't have this, it doesn't matter because we're going to substitute it out of there. Let's say 2 pi hw cubed over 3. Frankie, are we okay so far?
Yeah, I'm good.
Are you sure?
I think so.
Okay. Are you ready to differentiate? So that's going to be 16 pi dHw dt minus 2/3 pi times 3 hw squared dHw dt. So we know that the water is coming in, what did it say, at like 3 or something? 2. So that's the volume coming in. And then HW is just 1. So those guys can cancel out. 16 pi dHw dt minus 2 pi dHw dt is just going to be 14 pi dHw dt. And then we divide both sides by the 14 pi, and I think that gets us there. So again, like visualizing what's going on is hard, right? The sphere is always like basically touching the bottom of the tank and just expanding so that always half of the sphere is below the water line. That's tough to envision in your mind from the words, right? And then if you're able to get that, the tricky part was then figuring out that the volume of the water left in the tank is going to be like the equivalent cylinder of water minus out half the sphere that's taking up space that the water would otherwise be filling. If you got that far, it probably was able to get to the finish line, but it's tough to see it the first time through, to really like think through that. Is that it's okay?
Yep, thank you.
You sure?
Yeah.
Okay.
I'll get it.
Okay.
Eventually.
Yeah, look over it again. Like, it helps to read it again. And like redraw the picture and it'll start filling in, I think, a little bit. But this is one where like having a good imagination, like being able to see it in your mind, really makes a big difference. It's hard to come up with anything if you can't kind of see it, you know? This won't be the last time that like having some imagination to envision something will come in handy in this semester. What else do you guys want to talk about from, is there others from set 4 you want to talk about? This was the hardest one, I thought, by a good margin on set 4, just because of the setup is quite tricky. Okay, fair enough. Well, let's talk about 5.3 then. So in 5.3, we're going to look at something called the fundamental theorem of calculus. With a name like that, you might guess that this is a pretty important idea. So recently, these first 3 sections we've talked about antiderivatives, we talked about finding the area under a curve. The process we used to find the area under the curve we called an integral. Today we're going to link these 2 ideas together, because I had promised that we were going to tie this up into a nice neat bow. Today is the day when the bow gets knocked that guy nice and tight, and life is about to get much simpler for all of us, which is a good thing, right? Like, everybody likes that idea. So we're going to start with me defining a new function. So this function is g of x, which is equal to the integral from a to x of some function f of t dt. You want to think about this function as like an area up to x function, right? It's going to calculate the area under the curve up to some endpoint. Is everybody okay with that? So the area under f of x up to, starting at a and ending at x, where x is a variable, so it's going to compute all the possible areas under that curve and write it as like a function. What does this kind of sound like? Should kind of sound like a derivative, where the derivative is going to calculate the slope of all the slopes of the tangent line for a curve, right? This is kind of the same, an equivalent idea, where this is going to calculate all the possible areas under the curve. Everybody okay with that idea? So to just get a handle on this, about thinking about this as like an area function, let's say we have this function y equals f of t that's defined as this graph. We have our function g of x that's equal to the integral from 0 to x of f of t dt. And we're just going to evaluate this function at some values of x, 0, 1, 2, 3, 4, etc. Okay, and I'm just going to do a couple of them to give you the flavor of what's going on. So if I want g of 0, I'm plugging 0 in for x. So I'm just computing the integral from 0 to 0 of f of t dt. Since the start and end of my integral are the same, we know the area under the curve is 0, right? Everybody remember that? Okay. If I want g of 1, that's the integral from 0 to 1 of f of t dt. So it's like just that part of the curve. Well, that's a triangle, right? So the area under that curve is just a triangle. I can find the area of that triangle fairly easily. But feel okay doing that? And if I want to do g of 2, that's just the integral from 0 to 2. So that's a triangle, g of 1, plus this rectangle. Does everybody feel okay about what I'm doing as I'm doing this? Yeah, stupid thing. Okay. So if I go ahead and I plot my points, I'd like 0, 0, and like 1, 1, and like 2, 3, and I'm going to get like a curve like this for G. So like the y-axis is like the area under f of t, and the x-axis is like the end point for that area under the curve, right? Where we start at 0 and we're ending at 1, 2, 0, 1, 2, 3, 4, 5, etc. So I get something that looks like this. Is everybody okay with how I generated this graph? Just basically took the points I would have found in the previous problem and plotted them and kind of sketched a curve, right? So I want to ask myself, is there a relationship between the derivative of this area function, this g of x, and the function that I'm finding the area under the curve for, my f? So the long and short of it is, we're going to skip doing some of the idea. But the derivative of this area function is f of x. Think about what we just found here, right? You have this, right? I do the derivative of both sides, and I'm going to get g prime of x equals f of x. What is the derivative doing to this integral? Just, yes, canceling out, so I'm doing it. Wait a second. Wait a second, does that mean that they're like inverse operations? Like it's akin to multiplication and division where they cancel each other out? Or squares and square roots? Or arc cosine and regular cosine? Yeah, that is what we're saying. Yeah. So that statement is the fundamental theorem of calculus part 1. Is that integrals and derivatives are inverses of one another. So, does that mean that it works the other way? That like if I have g prime and I do the integral of g prime, let's see. Does that give me g of x then? And how did we go from g prime to g of x in 4.9? Antiderivative. So you're telling me then that the area under the curve is somehow just related back to this antiderivative thing. Right? Before we had a notion that maybe that was true when we did that like, velocity and time thing and looked at the displacement. But here we're seeing like, algebraically, we've got something here. Okay? So, continuing on, let's look at an example. So find the derivative of this function g of x equals the integral from 0 to x of the square root of 1 plus t squared dt. So that's what we're doing, right? What are we going to get? X squared, right? The variable has to match. So somehow in taking that derivative, right, t isn't actually the variable, this function, x is the variable. Right, t's like a dummy variable or whatever, a parameter. There's like a kind of a chain rule thing happening here that we'll talk about in future sections or later this semester, later this chapter even, that will make expressly clear. Is everybody okay here? And in fact, we'll do it on the next problem, this chain rule idea. Okay, so here it says find the derivative of the integral from 1 to x to the 4th secant t dt. So we have this is like our area function, right? Everybody's okay with that? That's what we're going to be taking the derivative of? Yes?
What did the x squared?
Oh, I swear I tried to write it. Thank you. Now, question. Is that the same thing? Let's just check it out with some test values, right? If x equals 1, I have g of 1 equals the integral from 1 to 1 to the 4th, right? If x equals 1, I have 1 to the 4th equals the integral from 1 to 1. Right? Okay, that looks good so far. X equals 2. The integral from 2, or I'm sorry, the integral from 1 to 2 to the 4th. If I go over here, I plug 2 and I have 2 to the 4th, so that plugs in here, right? The integral from 1 to 2 to the 4th. Are these the same thing? Yeah. Mm-hmm. 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 Now, the reason why I wanted to do that is because if I want to take the derivative of g of x to the 4th, what am I going to need to use? That's a composition of two functions, right? G of x to the 4th. If I'm going to take the derivative of a composition, I need to use the chain rule. Very good. So this is going to be the derivative of g of x to the 4th times, or I'm sorry, g of x times the derivative of x to the 4th, right? Okay. So the derivative then is going to be secant x to the 4th times 4x cubed. So I did the same thing where I'm just taking this and plugging it in to get the derivative of g. But because this here was like a function of x, I have the chain rule piece attached to it, right? This is like the inside. We talk about the derivative of the outside times the derivative of the inside. Does everybody feel okay with what I've done? Now here it comes. What's been the biggest hassle in our lives so far, at least in this class, this semester? Calculating this area under the curve, right? We had to do this limit of sums business, and remember all these summation formulas and all this mumbo jumbo? Yuckarooski. That ends here and now today. Fundamental theorem of calculus part 2. The definite integral from a to b of f of x dx is the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. What we've done is we've just tied a nice neat bow that tells us we can calculate the area under the curve just by using the antiderivative, which was much easier for us to calculate than this limit of sums business that we were doing in the last section, right? Let's do an example. Okay. I want the area under the function e to the x from 1 to 3. Using the fundamental theorem of calculus part 2, what I need is the antiderivative of e to the x. What is the antiderivative of e to the x? E to the x. And then I just need to evaluate this from 1 to 3. There's my answer. If you want a decimal, you can type that into your calculator. But I'm done. It's the antiderivative evaluated at b minus the antiderivative evaluated at a. How nice and neat was that? This was one we couldn't even have done using our summation formulas. We didn't have a sum for an e to the x, right? All we had was sums for like constant x, x squared, and x cubed. So really all we could handle up to this point was polynomials, and like rather low degree polynomials at that. Area under the parabola of y equals x squared from 0 to 1. That area is going to equal the integral. Now to compute that integral, we just need the antiderivative of x squared, which is I'm going to write it this way, x cubed over 3. Do you guys remember the formula for this? From 4.9. And then that has to happen from 0 to 1. How much time would it have taken to do that with the limit of a sum? Way longer than that, then, right? This is one you can virtually do in your head once you get comfortable. I mean, not right now. You're not comfortable yet. You haven't practiced really with it. But like, with 1 day of practice, that's an integral you can do in your head now. Okay? Let's do this one. So this says dx over x, right? How should I think about this? What is the f of x here? What function are we integrating? 1 over x, right? This is really, I want to think about this as that. What's the antiderivative of 1 over x? Natural log of x. Evaluated from only like $20 for babysitting.
Thanks. I'm telling you just about.
Evaluated from 3 to 6. What's the natural log of 6 minus the natural log of 3? No. Quotient property of logarithms says you can write that as 6 over 3. Natural log of 2. Close. What do you guys think so far? How much easier is this than limit of Riemann sums? Way better, right? Like, oh, they're just going to connect this back to the derivative formulas from first semester? It's really the same thing, just kind of going in reverse. Yeah, it really is. Oh, good. The area under the cosine curve from 0 to b, where b is between 0 and pi over 2. Do that, right? It's the antiderivative of cosine. Negative sine x, right? No. sine x. Sorry. So that's just sine of pi over 2 minus sine of 0. What's sine of pi over 2? 1. Sine of 0 is 1. Look at how nice this is. Isn't this lovely? Like just cranking through. Notice that all these problems, I'm doing the exact same thing, even, regardless of the wording. Right? Because I know an integral is the same as the area under the curve, and I can just kind of move back and forth between those two ideas fluently. Right? It's the same process. So, this is just summary, putting them both back together. And that was it. That was the day. What did we just do? We just related this idea of integrals, area under the curve, back to the antiderivative. And now I can use the antiderivative to calculate these areas, or I can use a derivative to cancel an integral, or I can use an integral to recover my derivative, right? All these processes kind of work in conjunction with one another. Yes, that's really nice. Questions? We're stopping here. This is good. And that. So, the takeaway, what part of 5.2 do you really need to have going forward for an AP exam? The part that you should be able to do is if I show you the limit of a sum, you should be able to translate that into an integral form. If I give you an integral form, you should be able to translate that into a limit of a sum. You do not need to evaluate that limit under any circumstances. I will not ask you to do that. The AP will not ask you to do that. Unless it's like, this limit is equal to this integral, which I do by antiderivatives, and I get my answer. Like, that's fine. I can ask you to do that. But no way am I going to ask you to evaluate the limit using like the definition of those summations and doing all that mumbo jumbo. Never going to ask you. Is that okay? So again, like section 5.2 was akin to when I made you evaluate derivatives using the limit definition. You're like, oh my God, this sucks. Am I going to have to do this on the test? I'm like, no, not really. Because just wait till the next section. And you get to the next section, you start showing me the derivative shortcuts, and you're like, why don't you show this at the start? And it's like, well, I understand how this works in order to get the conceptual pieces in later on, right? Where we're like, understand where the derivative is going to fail to exist, like why a corner or something poses a problem. If you don't understand the definition, can't do that. The same idea here. If you don't understand how we're building these integrals, you lose conceptual understanding, and the conceptual questions kind of pass you by. Like, we need to do that part, even though I'm not going to ask you to do the algebra. You need to understand how this thing, the machinery of how this thing is working, so that you can make predictions about what will happen if, without actually having to grind anything. Is that okay? Because eventually we're going to start having to look back and forth fluently between a function, its area function, the derivative of the area function, the second derivative of the area function, the integral of the area function, we're starting to layer these concepts on top of each other, and you don't have a good understanding of what is happening and how it's working. Those things become really difficult. Okay? This is the point in second semester where this transitions away from the theoretical into the mechanical. So like the theory, we built this integral, and now we're gonna learn the shortcuts, like the mechanical parts of like, okay, how do I do integrals if they're not like a direct antiderivative, you know? We'll work on how to do all those little circumstances and then start looking at applications of integrals, like what can I use an integral to do, what kind of real life problems can I solve with this thing. And that's basically second semester. The rest of the semester is devoted to, you know, like dealing with the mechanics of how I do this antiderivative process if it's not like a simple direct antiderivative like we had here. You know, like what if it's the reverse of a chain rule, or the reverse of a product rule, or even worse, like selected quotients, where I have to learn how to handle the mechanics of the antiderivative process for those things. Those are like multiple sections that I just kind of breeze through that we're going to have to learn how to do. It's okay. And we have a lot of application to deal with after. So we'll touch a little bit on differential equations, like when you take an implicit derivative, like you implicitly differentiate these related rate problems and you get like a problem with, you know, dv dt equals 2 dx dt plus 7 dy dt or something like that. We'll learn how to like solve that kind of an equation, i.e. recover this thing that you started with. That will use an integral. We're going to talk about how you calculate the volumes of irregularly shaped objects. So like if I have a funny looking solid, and how do I calculate the volume of this using an integral? Or if you are interested in a career in engineering, almost always you're going to be interested in like, I'm going to create a 3D model of this part that I need, and then I need to be able to calculate how much material I need to create this, like how much volume is this object going to have, this nut or this bolt or this fender or this whatever piece of some machine. We'll learn how to do that. Sounds exciting. That takes a lot of imagination, 3D imagination to picture what's going on to make sure you set up your problem correctly. We'll talk about work, like the physics sense of the word work, and how to calculate that, which is another accumulation situation where it's like that area under the curve so far. That's kind of the rest of the semester. This, in all reality, is the most difficult part, is what we've just done here, believe it or not. It's like laying the foundation for everything that we're going to build on top of it. Now, the mechanics of things coming next will be more complicated, right? But the conceptual piece, the understanding of it, like what's going on, will not be. It's going to be more like kind of doing algebra now. Okay? As an aside, total enrichment idea. So when we talked about, when we built the mechanics to do our integral, we built our rectangles from the x-axis, right? We built those areas under, or rectangles under the curve, right? That's called a Riemann integral. There's actually a second type of integral, not something you'd experience until you took like a, you know, like a real analysis class or something similar, called a Lebesgue integral, where you use the y-axis instead. The advantage being that the Lebesgue integral is more flexible if you have something with like infinitely many discontinuities. Remember we talked about how those things were not integrable? With a Riemann, that's true. With the Lebesgue integral can handle some of those that the Riemann would not, because you don't have any discontinuities. You know, if you have continuity on the y-axis, right, like all the y values are covered, even if all the x's are not, right? Like you can build something out of that. Anyway, I don't know, that's just like a total aside. So, when you're in your 4th year of your math degree, and you run, Kate's like, no, it's not gonna happen. And you run into this, you'd be like, I remember Mr. Kulik talked about this one day in class, when he was just kind of tap dancing in place, filling like 10 minutes at the end of the hour, talking about stuff. Yes, sir. Sure. You guys ready to stop? I can stop talking.
Yeah.